Implicit differentiation allows us to find the derivative of an equation when y is not explicitly defined in terms of x. Now, we may not know what this means because we're not typically accustomed to saying y is explicitly defined as an expression, so I'm going to show you. On the left-hand side, y is explicitly defined in terms of x, so this is called explicit form. So not only is this explicit form, but it's the only way that we can define y explicitly in terms of x. Now the second one, y squared equals x cubed over 4 minus x. Here we have y is implicitly, so this is an example when y is implicitly defined in terms of x. Now, I'll explain why. One reason is we have y squared equals x cubed over 4 minus x instead of y equals an expression in terms of x. If I try to put this as a y equals, I end up with y equals two different equations, the positive square root and the negative square root. And that is what also leads us to say that y is implicitly defined in terms of x. Now we can find the derivative of both an explicit form and an implicit form of an equation. Here's an example right here. Find dy dx of xy equals 1. This form right here is implicit form. So this is an example of implicit form. I can rewrite this as y equals 1 over x by dividing both sides by x, and now this is explicit form. And we know that y equals 1 over x is the same thing as x to the negative 1. We can find the derivative by saying dy dx is equal to the opposite of 1 over x squared. I think that many of us are getting much better with that, being able to do that faster. Negative 1 over x squared. Now remember that dy dx means your derivative in terms of just x, right? So your derivative in terms of x. Here's another example for you to try. Dy dx for x squared y equals 1. Try rewriting. And here we have not quite found derivatives using implicit differentiation. We're manipulating our given equation to write it implicitly and then finding the derivative there. Sometimes that's not going to be available. So go ahead and try this one. It is optional. You can rewrite this one. So we're just practicing the first example. And if you're joining me back, or maybe you're just waiting for me, y equals 1 over x squared becomes the derivative of y with respect to x, negative 2 over x cubed. And here we have in terms of just x. And this is great practice of differentiation. So go ahead and try this one. Actually, try the next two. Press pause, come back, and I'm just going to really just give you the right answer. Dy dx is equal to negative 3 over x to the 4th. Look at this. This is just x. Dy dx is equal to negative 8 over x cubed. And once again, we've got it in terms of just x. In terms of just x. So you're probably saying, okay, well, what the heck? Why do we need implicit differentiation? Why are we even doing this lesson? Well, here you go. You cannot easily rewrite. So this equation cannot easily be rewritten explicitly for y. Explicitly for y. So what do we do in these situations? This is where we need what we call implicit differentiation. And it looks probably a little bit more challenging than it is, but differentiation takes place with respect to x. Remember that. Differentiation takes place with respect to x. This is an important concept for you to be thinking of and to be reminded of as you're doing your differentiation. So I'm going to write that here, like dy dx, the derivative of y with respect to x. So as you were listening to me, and sometimes you'd even say, can I write y prime? Well, sure, you can write y prime, but there were many times where I wanted to go back to dy dx, and that was because I wanted to continue to say the derivative of y with respect to x. And that's because this part is very important here. Okay, differentiation. We're going to differentiate each expression. So we're going to take it back to basics so you can see what I'm talking about. When we differentiate this expression, we're differentiating this expression with respect to x. So this is not an equation. When I put y equals 3x squared, we're taking the derivative of both sides. So this is what I'm doing. I'm doing this, dx. So that's going to be dy dx on the left, and then the derivative with respect to x of 3x squared. Do you see that? That right there is so cool. It's so cool. I'm just going to kind of leave it there because what we're doing is we're just doing the derivative of the right-hand side now. So the derivative of the expression with respect to x is equal to, we know this, it's 6x. So why do we need to know all this stuff on the left? Well, it all comes back to this with respect to x. So let me show you here. On the right here, we're going to take the derivative of 2y cubed with respect to x, right? The derivative with respect to x of 2y cubed. It's a form of the chain rule. So the derivative of 2y cubed is 6y squared. And then we're going to take the derivative of that y with respect to x. And there we go. So we've got our 6y squared times dy dx. That's our answer. When you take the derivative of an expression that involves just the variable y, and you're taking the derivative with respect to x, that's your derivative. So let's look at here, x plus 3y. And you'll get the hang of it, x plus 3y. So we're going to differentiate each term. So I've got the derivative with respect to x of x, right? Plus the derivative with respect to x of 3y. Well, the derivative of x with respect to x is 1, and the derivative with respect to x of 3y is the derivative of 3y times dy dx. So our answer is 1 plus 3 dy dx. Let me just write it there. That's our answer. Now here we're going to need our product rule. So I'm going to change my color here because we want to show you just a little difference here. Here I have to use my product rule. So the derivative with respect to x of xy squared is going to be the derivative of x with respect to x, which is 1, times the second factor, y squared, plus the derivative of y squared with respect to x. So the derivative of y squared is 2y times dy dx, times the derivative of the first, which is x. So the first term is y squared. The second term is 2xy dy dx. And that is implicit differentiation. So let's find the slope of the tangent line to the relation x squared plus y squared equals 4 at the given point, square root of 2, comma, negative 1 over square root of 2. Now when I put a square root of 2 in for x, and a negative 1 over square root of 2 in for y, it should make this equation true. And I'm not sure it does. Let me see. Let's see if it does. Let's see, the square root of 2 squared plus negative 1 over the square root of 2 squared equals 4. Is that true? 2 plus, this would be 1/4 equals 4. That's not true. So I believe that this needs to be, actually, you know what I think that they're saying here? Find the slope of the tangent line to the relation. Yes, I changed it. Okay, I'm not sure if I changed it on your notes, but I did change it on mine, because this right here, I didn't want to change the point. It was the equation that needed to be changed. Let's see. So there we go. So you need to change that equation. That's the equation right there. X squared plus 4y squared equals 4. And I believe that maybe it's 2y squared. Let's see. Square root of 2. I think it should be 2 squared. Square root of 2 squared. This is actually very important because this point needs to work in the original equation, right? Yes, because when I square this, it's not 1/4. You're probably trying to stop me there. This is 2 plus 1/2. So yeah, we're going to have to multiply that by 4 to get it to be 2 plus 2 equals 4, and there's our 4. Good. Okay, so that's the equation. I apologize that that 4 wasn't there for you, but this point needs to work in the original equation. We want to find the slope of the tangent line to this relationship, or to this relation, which is a circle. Now, think about this. It's actually an ellipse, but it's circular, so it's a relation, not a function. Find the slope of the tangent line. So remember, slope is derivative, so we have to find the derivative of this equation with respect to x. So I'm going to find the derivative with respect to x of the left side and the derivative with respect to x of the right side. So the derivative of the left side with respect to x is 2x plus, and then the derivative of 4y squared with respect to x is 8y times dy dx. And the derivative of 4, we know, the derivative of any constant is 0. I'm going to subtract 2x from both sides. And the reason I'm doing this is because I need that derivative, and that derivative is dy dx. So I'm going to solve for dy dx. So now I'm going to divide both sides by 8y, and I need a little bit more room here. Dy dx is equal to negative 2x divided by 8y. So we just solve for dy dx. We can reduce the negative 2 and the 8 if you'd like, or we can just keep them where they are right now and reduce later. It's all about this x and y though. This x is this x, and this y is this y. So now it's really important when we plug that numerical value in to find the numerical slope, we have both values from the ordered pair. Now I'm going to, when I rewrite it, I am going to reduce. This is negative 1 over 4. And then in for x is the square root of 2. and n for y is negative 1 over the square root of 2. I know I'm going to have a negative over a negative. So I've got the square root of 2 divided by 4 over the square root of 2. And that's the same thing as the square root of 2 times the square root of 2 over 4. So that's 2 over 4, which is 1/2. So our slope is 1/2. And that was exactly what we needed to find, so I can box that answer and be done. If I needed to write the equation of the tangent line, I'd have to go one step further and use that point and slope and write my equation. Here's one for you to try. Nine plus 16 is 25, so 3 negative 4 is a point that is on the relation x squared plus y squared equals 25, which is a circle, not a function, because it's a circle. Go ahead and find the slope of the tangent line, and then come back and check your answer. Okay, I'm showing my work here. So you can compare. And I got 3/4 as my answer. Okay, we're going to come back in the next video and we're going to finish up with some more examples, continue to get practice with finding our derivative with respect to x of implicit forms of an equation.